Hi class, welcome back to our continuations of the lectures on quantum mechanics. And again, our reference for this lecture, or actually for this lecture series, is Introduction to Quantum Mechanics by David J. Griffiths. And this book is highly recommended for you. So to continue with our discussion, let's go immediately to electron in magnetic field. A spinning charged particle, or electrons for example, constitute a magnetic dipole, and the dipole is in the z direction if it is spinning counterclockwise on the xy plane. Its magnetic dipole moment is proportional to the angular spin. Angular moment or spin angular momentum S, and this is just this one. When a magnetic dipole is placed in a magnetic field, it experiences a torque. And this torque is just given by mu cross the magnetic field. And this torque will tend to align the particles or the charged particles parallel with the field or the magnetic field. And the energy then associated with this torque is, of course, equal to H equals negative mu dot B. And so with equation 4.156, you will have H is equal to negative gamma times the dot product of B times S. Here, S is a matrix and B is a vector. So let's proceed with the example for the Larmor precession. Imagine a particle of spin 1/2 at rest in a uniform magnetic field which points in the z direction. So you have the field to be equal to B equals some constant B sub O times K, where K is the direction of the field. So now the Hamiltonian matrix, therefore, or the operator, the Hamiltonian operator, therefore, would be equal to this one. Since your SZ would just be this matrix. So if you solve for the eigenvalue and also the eigenvalue and the eigenstates, we actually know that, or we have actually solved that in the previous video. It's just chi plus, where chi is equal to chi plus is just equal to 1, 0, and chi minus equal to 0, 1. So the chi plus has energy E plus equals negative gamma B sub O H bar over 2, and the other one has energy equal to positive gamma B sub O H bar over 2, the spin down or the spin down state. So anyway, the spin 1/2 particle will have spin up. This is spin up also. spin up, and this one is also spin down. The energy is lowest when the dipole moment is parallel to the field, because it's a dot product, and if it's parallel, the angle between the magnetic field and the mu would be 0, so you have negative mu b cosine 0. So it's the lowest energy because it's negative. So we can now go back to the Schrdinger equation. This is the time-dependent Schrdinger equation, the DSE, but your state of the particle would be the spin state, this one, so that you can replace the chi there with this one here. And here you have two states, spin up and spin down, and spin up has this energy, and this spin down has this energy. By the way, you can of course the A and B coefficients here are the probabilities that the particles spin 1/2 would have to have a spin up or spin down. So their probabilities, when you square A and B, should add up to 1. So we can say that A and B could be equal to cosine alpha over 2, and B is equal to sine alpha over 2, since when you add them, the square of them just would result to 1. So here, later we will know the significance of the alpha. So you can write the general spin state of spin 1/2 particle into this form: cosine alpha over 2 times the exponential of I gamma b sub o t over 2, and the bottom element would be sine alpha over 2 e to the negative I lambda b sub o t over 2. So how can we calculate now the expectation value of the spin S as a function of time? First, we have to get the expectation value of S of x, and then S of y, then S of z. Then we just add them. The square of the expectation value of S of x plus the square of the expectation value of S of y, and of course the square of the expectation value of S of z. You add them together and get the square root of that. That would be the expectation value of the S. So to get the expectation value of S, we use this formula, which is of course that's the formula to get the expectation value. Because these are, you don't use integrals here, because these are matrices, so you just have to do this. Because in the integral, if you get the expectation value of something, for example x, this is integral of psi star x psi dx, for example. And here you're dealing with matrix, so the formula would just be this one. So similarly, when you operate this, you operate this one here, This is your Sx. This is your chi. So you will have to deal with matrix multiplication from the left, from the right to the left. You multiply from the right to the left, and you will get this as your expectation value of Sx. Similarly, your Sy would be this one. By the way, these are the definition of Sx, Sy, and Sz. As we have I cannot erase anymore. This is your Sx, your Sy, and Sz. You just substitute that to get the spin expectation value. Here. So you have for Sy, you just use the matrix equivalent for Sy, and then for Sz you will get this one also as the expectation value. So when you get the expectation value of S, this one, it's necessary to get this expectation value of Sx, Sy, and Sz first. So here you can see that the expectation value of this x component of S has this term, and also for Sy you have this term, and for Sz you have that term. So evidently S therefore is tilted at some constant angle alpha to the z-axis. Look at the z, you have cosine alpha here. So S would, if S is this one, and your Sz would be, this is alpha, and your Sz is here, so Sz would just be some cosine component of your S. Your S here is actually h/2, and so you can see that it's tilted. The figure is here at the bottom. Alpha. And this S will have a frequency, it will revolve around the z-axis, the tilt will revolve around the z-axis with frequency omega equal to y b sub o, and this one is called the Larmor frequency. That is the Larmor frequency. So that's for that example, and then we go to the next example for the Stern-Gerlach experiment. So in an inhomogeneous magnetic field, there is not only a torque but also a force on a magnetic dipole. Here, if you can see this in this figure, by the way, before that, the force on a magnetic dipole has this form. This is the differential of mu times B is the energy. So this is the differential of energy, which is the force, just the force. So in this figure, you have a beam. Say for example, if this beam is an electron beam, they will separate. If you have a magnetic field here, so there's a presence of magnetic field, it will pass through a magnetic field. What happens is that this beam will be separated into spin, categorized into spin. They will split up, spin up and spin down. For example, if you have an electron beam, but if you have other beam with other spins, it will separate into a band where the band will have a difference of h bar, or will have an integer difference in spins. So for example, if you have spin S2, then it would, this is like for spin 1/2. If you have spin 2, then it would separate into five beams with different spins. Like this, for this one you have 2, 1, 0, -1, -2. So that's that's the Schrdinger experiment. So when you let it pass through a magnetic field, the beam will separate itself, and you will see that there are degenerate states in that beam. They have the same energy, the beam has one energy, but has different spins. So I'll just show you this slide. I'll let you read the slides, then I'll let you explain what this experiment is all about. So just screenshot the slides. This is the Schrdinger experiment. Review the slides of this experiment, and then I'll let you explain this in detail. You can also do some research on this. This is an old experiment, by the way. So let's now proceed to addition of angular momenta. Suppose now that there are two spin 1/2 particles, for example, an electron and a proton in a ground state of the hydrogen. You have a system where there are two fermions. By the way, fermions are spin 1/2 particles. So you have an electron and a proton. The electron could possess spin up, and the proton could also possess spin up at the same time. The electron could also possess spin down, and at the same time the proton could also possess spin down, or they would have different spins. One is up and one is down. So, question is, what is the total angular momentum of the atom? So, there should be, like, if you have 1/2 and 1/2, one total spin would be 1, and the other total spin would be 0, and the other total spin would be -1. What is the total angular momentum of the atom? So let's let the the spin to be equal to this. The first one acting on the first particle, and the second one is acting on the second particle. So you have two particles, so there are two states. This is for the first particle, and this is for the second particle. And you operate Sz, or the spin z, on the particles. So since there are two particles, so you have Sz of Sz to 1 plus Sz to 2 on chi1, chi2. Of course, Sz to 1 will just operate on chi1, and Sz2 would just operate on chi2, Sz to 2. So this is just this one and this one. So Sz chi1, no, this is not X, this is chi, sorry. So Sz to 1 chi1 would just be Hm1 chi1, and this one would just be chi1 Hm2 chi2. And so you have the eigenvalue of H times M1 plus M2 times chi1 chi2. Chi1 chi2 would just be the state of the atom. So as I've told you, if this is for the electron and this is for the proton, then they could sum up to 1, 0, and negative 1, because they have 1 half, 1 half, 1 half, negative 1 half, negative 1 half, 1 half, and negative 1 half, negative 1 half. So they have 1, 0, 0, negative 1. Let me just so now here, look, there should only be 3 states, because you have 1, 0, supposed only to have this one, but this one has 2. There should only be one state in which, or there should only be one scenario in which the proton and electron would have spin 0. And how do we get that? How do we get this? Then we just have to apply S minus, the lowering operator, S minus on this state to get the lower state of that. Or we can also apply this S plus of this one to get the upper state of this, because we're supposed to have this one and this one and this one. But this one we are yet sure, because there are 2 possibilities for that, but we'll just look at it now. So here, if you apply this one here, then you would get this state. This is exactly what we're looking for, the combination of these two. it's not separate, but a linear combination of these two states, which has an angular magnetic moment 0. So then we can say that evidently we only have three states. One is spin 1, one is spin 0, and the other one has total spin of -1. And therefore the atom so spin 1 is a triplet, by the way. So it can have in any of these states. This is called a triplet combination. So when your spin is equal to 0, it has only 1 m. It only has 1 m, and that m is also just equal to 0. You can't have 0, -1, because this should be the largest. This value should be the largest m, so -1 couldn't be this is your S, this is your m. So your m would not be beyond the absolute value of S. So here, or the absolute value of m could not be beyond S. So for this case, you only have a single state for 0, 0, for spin 0. So this one is called a singlet. A singlet. So if you apply S plus, it will give you 0, or if you apply S minus to 0, 0, this will just also give you 0. The triplet states are eigenvectors of S square with eigenvalue 2h bar square, and the singlet is an eigenvector of S square with eigenvalue 0. So S square, by the way, is just equal to this. For two-particle system, this is just S square. And using 4.142 and 145, that's already in 142 and 145. That's in the previous lecture, but let's look at that anyway. Here, unfortunately I can't erase this one, but yeah, you have the eigenstate relations between spin, between the eigenstate or the eigenspins. So anyway, let's proceed with this. So if you apply S1 dot S2 to this state, then you would have S1x Sx to 1 applied to spin up times sx to 2 spin down plus sy to 1 spin up times sy to 2 spin down plus sz to 1 spin up and sz to 2 spin down, and you will have this result from 145, and this one will just give you h bar square over 4 times 2 times this combination of spins. And similarly, if you apply to this state, you will have this result. There's a difference here and here. So you have to be careful in doing such calculations. So therefore, for S1 dot S2 this is 10 is what? 10 would just be equal to this one minus that one. Look at it's plus, sorry. So look at this, you have a combination, and when you substitute that here, you will get this one. And for the singlet state, here you will have just 3h bar over 4, this one here. And so therefore s square, so if you apply this to S10, for example, here, that would just be equal to, so of course this one is 3h bar square over 4, this one will just give you 3h bar square over 4, this one here, and also this one 3h bar square over 4, and this one is h bar square over 4. So here you have that, and then you will have 2h bar square 10. So the eigenvalue of s square is 2h bar, and this is the eigenstate, same eigenstate. And for s square 0, this will just be, so this one is 3h bar square over 4 plus 3h bar square over 4 minus twice this one, and that's here. So this is now equal to 0. So the eigenvalue of s square on the singlet state is 0. So in general, if you combine S1 and or if you combine a particle with spin S1 and spin S2, the total spin S that you can get is this. So there are many spins that you can get. So for example, if you have 3 halves and 2, for example, that would be how many spins that you can get? You have 7 halves, 5 halves, 3 halves, or 1 half. For this, you have 2 states, spin states for 1 half. This one has 1 half and negative 1 half. This one has negative 1 half and 1 half. This one has negative 3 halves, negative 1 half. You have 1 half and 3 halves. So these are 2 states, these are 4 states, these are 6 states, and this one has 8 states. So that's when you add S. Of course, S has different M's, no? So the state is always represented by that. And so if you have 5 here, and here you have 5, 0 is a state, 5, negative 4 is a state, is a spin state, I mean. So there is like 11 states for spin 5, for example. So that's it. So now, if a hydrogen atom is in the state phi NLM, the net angular momentum of the electron spin plus orbital is equal to L plus 1/2 or L plus or L minus minus 1/2. So, let me just discuss this to you, the Clebs-Gordon coefficient. So, if you have a particular state or spin state, Sm, with total spin S and Z component M, then that spin state is a linear combination of the composite states S1 M1 and S2 M2 here. This one, linear combination. And this one is given by the Clebs-Gordon coefficients. So the Z component they add up. Only the composite states that contribute are those for which M plus M2 equals M. So here only the states that contribute to this let me erase. Only these states in which M1 plus M2 equals M contribute to this total spin state here. So let's take an example. So like this one, equations 4.177 and 4.178 are cases with S1 equals S2 equals 1/2. So this one is spin up and spin down. Let's look at that. Here. Because S1 S1 M1 could be positive 1/2, so they add up here and here. And of course, they could also add up to 0 if their signs are negative. So let's look at the Clebs-Gordon coefficients. A square root sign is understood for every entry here. Let's enlarge this one. This is already the maximum size, sorry. This is the Clebs-Gordon coefficient. So if you can see this, I'll enlarge each of these sets and then you can screenshot. And reconstruct this. We also have this one. Just screenshot it. And this one. And we also have this one here. So anyway, let's take a look at an example. For example, the shaded column of 2 by 1 table tells us that 2 by 1. So that's here, that's this table. This is 2 by 1 and this is the shaded part. So look at this. We have two and 1 negative 1, 2 1 negative 1. There is a probability of 1/3. So here it's written 1/3, but it should be square root. This one should have a square root of 3. So that's the first contribution. The second contribution would be 2 1 and 1 0 with probability of 1/6 or a square root of 1/6. Square root of 1/6 or 1 over square root of 6. That's 2 1 and 1 0, and this is the probability, this one here. And the other one is 2 0 and 1 1 with probability of negative 1 over square root of 2. So that's how you decompose this spin, using the Clebs-Gordon table, using this table here. And so if you would try, like for example, how would you decompose this? How would you decompose this spin, for example? If you would like to use this one here. So that's easy. You just follow the example, the procedure in the example, and then it's already okay. And also if you add up the squares of the probability, here you have 1/3 plus 1/6 plus 1/2 is just equal to 1. The square of the coefficients. So here, the shaded row in 3/2 by 1, 3/2 by 1. If you want to multiply or two spins, for example, this one, for example, here, two spin states, S1M1 and S2M2, then it would also result to a linear combination of spin states. So for this one, you have 1/2 here and 0 here. Then all of the states should have m is equal to 1/2. So this is 1/2, this is 1/2, and this is also 1/2. But the S would be, of course, different. It's different, and you can see the contributors to this multiplication of spins will be given by the Clebs-Gordon coefficients. So here you have, for this one, you have 1/2, 0. You have 3/2. So you have 3/2 by 1, and you have 1/2, 0. So this is three halves by 1 and 1/2, 0. And then you follow this. This is just square root of 3/5, and then you have this spin state, square root of 1/5, square root of 3/5, and this state, square root of 1/15, and this state, and square root of a negative square root of 1/3, and this state. So you will have this one. So again, the probabilities will add up to 1. So that's it for this lecture, and I hope that you've learned something. And I will be posting the assessment for the Monday and for the first and this lecture of the week. So just watch out for that in our Google Classroom or in our Molly Classroom. So see you in the next chapter. The next chapter would be quantum statistical quantum mechanics. So that's the next chapter of this lecture series. So that's it. See you next time.